So it looks like we're finishing off section 6.2. We've got two things to talk about. One is how the binomial distribution can come up with a simple random sampling. And the other one is using the binomial distribution and the empirical rule together. We'll see those two things happen. Here's simple random sampling in a nutshell, I suppose. Choose a simple random sample of size n from a population with proportion p of successes. So you're sampling, and it's either yes or no for each individual. Maybe you're looking to see if they voted or not. Maybe you're looking to see whether they passed a class or not. Maybe you're looking to see whether a rock can be lifted or not. Maybe pick a thing. So it's a yes or no thing. When the sample is less than 5% of the population size, the count x of successes in the sample has a very nearly binomial distribution with parameters n and p. So we've got p successes, proportion p successes in the population. So if you just sample, say, one item, the probability of selecting that item that's a success, the probability that item is a success, is p. But as you continue the sampling process, if you take out successes, then there's less successes left over, and so the probability of success goes down if you collect successes, and the probability of success goes up if you collect failures. So to keep that from influencing the results and make it seem like a binomial distribution, we don't want that probability to change too much from go to go. So we can arrange that as long as the sample is less than 5% of the population size. You never pull enough out of the population to change the proportion in a way that it will influence the outcome, and so it looks like you're sampling with probability p at each juncture, at each sample, and so you get a binomial distribution with parameters n and p if you count successes. That was a mouthful. So here's an example. Suppose 8% of tomatoes shipped to King Soopers are unfit for sale. In a simple random sample of 10 tomatoes, count x equal the number that are unfit for sale. So x should have a binomial distribution. N is 10, p is 0.08. Write that down here. Binomial n equals 10. 8% is 0.08, like that. And we want the probability x is 2, so we're going to just use the binomial formula. 10c to 0.08 squared, 0.92 the eighth. That's 1 minus 0.08. Remember how this worked. It's n c k p to the k, 1 minus p, the n minus k, like that. So n is 10, p is 0.08, and k is 2 here. And I'll go ahead and do that. My calculator, trusty calculator here. We'll go into math prob. Hang on. I'm going to type 10. 10 math prob NCR. Having troubles today. Try it again. 10 math prob and then 2. And then enter. 10, choose 2, go. So that's 45. And I'm going to multiply that times 0.08 squared. And I'll make sure I go over before I hit the times button. And then 0.92 to the eighth. Okay. I get 0.1478. Find the mean and standard deviation of x. So the mean is NP. So that's going to be 10 times 0.08. And 10 times 0.08, lo and behold, is 0.8. Now remember, the mean doesn't have to match a possible value for the binomial distribution. The binomial spits out whole numbers. The mean is what happens if you average the values over many repetitions of the experiment. And since it's only 8% of the 10 come out to be unfit, when you average them over a long period of time, you just get 8% of 10, which is 0.8 as the average number of unfit tomatoes in 10 over many trials. And sigma is the square root of NP 1 minus P, like that. So I'll go, N is 10 times 0.08 times 0.92. 10 times 0.08 times 0.92. And then I'll take the square root and get 8579. Okay, did that. So, okay, that makes sense, I guess, to some extent. There they are. We just use the formulas for the binomial distribution with sampling tomatoes with simple random sampling of size 10 with success rate 8%, which is 0.08 as a probability. And then over here we go binomial and the empirical rule. It says binomial distributions have a bell shape if NP times 1 minus P is at least 10. That's our rule of thumb. So the empirical rule applies. And now we're going to use it in this coin tossing experiment. Toss a coin 1,000 times. Would 580 heads be considered unusual? We're going to compute mu plus 2 sigma, because we know anything more than 2 standard deviations above the mean happens around only 2.5% of the time, because it's the 95% encompasses plus or minus 2 sigma. The two ends carry the 5%. The one end above mu plus 2 sigma would be 2.5%. 5% is considered unusual, and by 2.5 is even more unusual. Okay. So we find the mean for this situation. It's 1,000 tosses, and the probability of heads is 0.5. So the mean for the count of heads is N times P is 500. So on average, you get 500 heads. I knew that. And then sigma will be square root of NP 1 minus P. N is 1,000, P is a half, 1 minus P is a half. So you get 1,000 divided by 4, 1,000 divided by 4, which is 250. And then we take the square root of that. And I get 15.81. Hey, I was right. That's kind of cool. And then we compute mu plus 2 sigma and see how it compares to 580. So 580 is above the mean. Is it far enough above? Is it more than 2 standard deviations above? So mu plus 2 sigma is 2 standard deviations above the mean. That's 531. 580 is a lot bigger than that. You might think, well, it's 80 above the mean. How many standard deviations is that? About 5. So it's actually really unusual because it's 5 standard deviations above. If this is following a bell shape, there's almost nothing allowed past 3 standard deviations. So this value would be considered very unusual. Unusual enough to break the 2 standard deviation barrier, but actually does worse than that. So there we are. A little more statistical thinking and a little more computing with binomial probabilities and mean and standard deviation. And that, in theory, is the end of 6.2.